All right. Good morning, everyone, and welcome to this event of part of the 7th CAPS NVIDIA workshop in accelerating applications using GPUs. And today we will focus on OpenACC. It's one of the programming models for accelerated computing. And we'll go through initially the some set of slides on introduction and to understand a bit what is OpenACC and how it works. And actually the same examples that I've shown in my slides, we will do it live on NVIDIA DLI platform, as you can see here on the left of my screen. And we will go through the exercises. We have few modules to go through today. Hopefully we can finish that within this morning. If not, we have a little bit time more in the afternoon. If you want to complete it, if you have questions and any discussion that we might have. All right, so let me get started on the slides here. Let me put that in full screen. All right. Hopefully that works well. You can see it properly. And as you can see in the title, it's a directive-based programming model. So, and as you can see in my shirt, it's more science, and the back of my shirt is saying less programming. So we do the minimum amount of programming using directives to get the most possible science, and at the same time getting an accelerated computing on GPUs. I'm Saber Feki. I'm scientist lead at Supercomputing Core Lab, and I'm DLI instructor, certified instructor in OpenACC by NVIDIA. And we're gonna go through this today. And before we go into the programming model, it's important to understand at least the basics of the architecture of a GPU. So the main things that you need to understand are more in the second slide, but even this slide is important to see that you have a bunch of SMs, we call them SMs, those are the streaming multiprocessors, and each one has a large amount of CUDA cores. And now in the latest one, we have 2 tensor cores for AI. Now they all share an L2 cache. There are memory controllers to communicate with the high bandwidth memory called HBM, and each SM has its own local caches as well. So that's, and there are some graphics, additional features, as it is a GPU by design. All right. But most importantly, those are the key things that you want to see. You understand on a GPU server what you're gonna get. So GPUs are accelerators, right? So they are PCI Express connected. PCI is a bus commonly used in latest processors, and it's bus that communicate the CPU or the processor to a network link, for example, network interface communication for the NIC. That's an example of a 200 gigabits per second InfiniBand HDR. On this case of this server, you can connect it to NVMe SSD, non-volatile memory. But also, most importantly, which is the topic of our class today, is to connect to PCI Express GPUs. And you can see here, those are the latest A100 GPUs. That's an AGX card with 4 GPUs. And they have by 16 connection of PCI Express to the CPU. Now, this is a very important consideration for us, because as you can see, the memory comes and we start the program on the CPU, and as you start accelerating code, you will need to move data from the main memory of the CPU to the GPU memory. And that transfers of data happens through the PCI Express. Now, if you look at some of the PCI Express specifications, we started with PCI Gen 2 in the 2010-ish, and then Gen 3 lately with the Voltas. And with A100, the latest Ampere GPU from NVIDIA, we moved on to PCI Express Gen 4. And that's significantly more powerful, even doubling the performance of previous generation. And still, even with that, there is a clear disproportion between what the PCI Express can offer, in this case 50 gigabytes per second roughly, theoretically, and slightly less in reality if you measure it. And if you compare it to the CUDA cores, that you have thousands of CUDA cores on the A100, achieving a performance of at least 9.7 teraflops. If you're not using CUDA cores, if you're not using tensor cores. If you're using tensor cores, it can go even up to 18. So that's even higher flops rate. So you need a lot of bandwidth to feed that engine, that powerful engine, with data to crunch at that speed. And remember that even on the 80 gigabytes per second, the latest one announced in last SC a few weeks ago, you can reach a performance of 2 terabytes per second of memory bandwidth within the GPU. So there is clear disproportion between this 50 gigabytes per second and the tremendous power of the GPU in terms of flops and memory bandwidth. So that's a consideration that we need to take care of, and we will be focusing on that on some of the exercises. In my slides, you will see some of the common mistakes that we've been doing. Now the latest compiler actually provide more additional features and can have a significantly better management of the data. All right. Now, let's see the real thing. So if you look at it, in reality, this is a GPU card here that you can see it's very small. Those are the PCI Express connectors, but typically we don't use one on the system except if it is a desktop, but we pack a lot of them. 4 to 8 GPUs are common. So this is a DGX system from NVIDIA, and you can stack 8 GPUs. So the GPUs are here, and that's on top of them the heat sink to reduce, to take off the heat from the CPU, from the GPU. All right, now how to program this beast. So there are typically 3 main models to program these GPUs. The first one is using parallel programming models custom made for this program, for this device. The first one that was commonly used was CUDA when the first time GPUs were introduced to general computing, becoming general purpose. After that, there are other programming models and languages such as OpenCL. But then slowly in the future, we expect that even standard languages will have some acceleration within, such as C++, newer standards, and even Fortran. So we'll keep looking at that, but that's what I mean by it's just simply programming for the GPU explicitly. And there, it's very similar if you can have the analogy to something like assembly, because you literally need to write every instructions to move data from memory of the CPU to the memory of the GPU using CUDA mem copy. You need to allocate on the GPU specifically, and so on and so forth. And you will see that on OpenACC, for example, you don't need to do any of that. Very few pragmas and you are up and running. And that's the second model, which is using directives. In the beginning, the only directive-based was OpenACC, and HMPP actually before that. But then there is convergence toward the standard, and OpenACC was standardized, which is based on directive. And lately, after that, starting OpenMP5, we started having a GPU offload to accelerators using OpenMP. But OpenMP and OpenACC are slightly different. And if you want me to put it in one sentence, so OpenACC is more descriptive, in the sense that you describe the parallelism that you wish to expose to the device, use that and rely on the compiler to understand whatever you describe in terms of parallelism, and you run it on the accelerators. So it's descriptive. Now, OpenMP is, however, prescriptive. So you give clear instruction and exactly how the compiler should do it, which is a slightly different model. So you get a lot of more responsibility as a developer when you are using OpenMP than OpenACC. Last but not least, and most importantly, which is common thing that is being used across before, which is libraries. So as you can imagine, with directive-based, you may not get the best juice and the best performance that you can get from a very powerful accelerator. So programming languages, if you write something, some routines explicitly with very much skilled people, ninja developers who extensively optimize some routines, such as numerical libraries and so on, those can be very useful and exposed. And NVIDIA is providing us with tons of those libraries nowadays, some for typical computing, some others even for AI and other workloads. So the other aspect that I want to capture in this last comment in this slide is that it's not only one way. You can even mix and match some of these programming models as they are interoperable. So you can have a CUDA code where some of the routines will be with OpenACC and some will be calling libraries, so on and so forth. So we'll see an example maybe potentially on how that can happen in the case of OpenACC. All right, moving on. So I mentioned before that OpenACC is a standard, and what does it mean is that basically in the 2011, when Titan was introduced as #1 supercomputer, the DOE requested an open standard programming model that is easy to use. And at that time, NVIDIA collaborated with Cray, who is the manufacturer of Titan, PGI, a software company that had some accelerated component in their compiler, and CAPS, who had HMPP at that time, which is a similar directive-based programming model. And as you can see, those three companies are red now because Cray was bought by HPE, PGI actually got included and bought by NVIDIA. Now they are part of the same software ecosystem. And CAPS actually is out of business, I believe. So nonetheless, OpenACC growth, it's a standard that is available and keep releasing the new releases of the standard with more functionality, adapting to the requirements of the developers over time. Now they have 33 members. KAUST is proud to be part of these academic members, which are non-voting mostly. But still, it's very important to have access and influence to the standard and understanding and contribution as well. One of our contribution is one of the chapter books on the first book of OpenACC that was released a couple of years after the standard is there. All right, so why OpenACC? There are three main advantages. One is it's the primary use of directives, which is the easiness. So it's easy to use, an easy path to accelerate computer science applications using simple directives that you can insert in your code. Then it's open. It's an open standard that is available to everyone. The standard is now not only implemented by one compiler, which is PGI/NVIDIA, but also other compilers now started implementing OpenACC. And the most prominent one is the one that is used by most of the academia, which is GCC. So GCC supports OpenACC standard, and that's fantastic. And there are other commercial compilers, I believe, Backscale or some others. So, that's very important because now you have a single code that can be compiled with different compilers. It's open standard and you can run it not only on GPUs, but any accelerator platforms, including multi-cores actually. And that's fantastic because that allows portability across platforms. And that's a very important aspect of OpenACC. It's also powerful because those directives actually give you a complete access to the power of GPU at different levels of parallelism with different features of the GPU from scratch. The architectural details can be expressed on using just directives of OpenACC. I will go through a couple of slides very quickly through some research we've done in 2014 when OpenACC started. Very simple, actually, when we had CAPS and PGI as two compilers there. And you can see here that at the beginning, you need to have a little bit different coding to get the best performance out of them. So you can compile both codes with both compilers, but you have a better performance on CAPS using that version, a better performance on PGI using that version. That was a nice analysis we did using an electromagnetics code with collaboration with Professor Hakan Bakshi. And the results are, you get similar performance, more or less, and as you have larger degrees of freedoms or larger data sets to crunch, then you get better performance acceleration. Now, let's dive in and how we write OpenACC. So it's based on directive, and the basic directive that we use is ACC directive, and the name of the directive here in Fortran. And of course, in Fortran, you have to start in close since you don't have these curly brackets like you have in C. But in C, you have these curly brackets or loops and structured code with beginning and ending clearly seen in the code. Then you use the hash pragma ACC and then the directive name. You can see here there are optionally you can add clauses. So there are not only directives of OpenACC that you're gonna choose from, but also there are clauses that are additional annotation that you can add to the line of OpenACC. So the first OpenACC directive that we want to learn is kernels. And basically, if you put an ACC kernels, and that's a Fortran example I start with, what happens is that those loops, two loops, actually will be executed as separate kernels, and each kernel will be parallelized and executed at acceleration on the GPU. So from this code, we need to start compiling, and that's a Saxby example here. And the compilation use the PGI compiler. We will see that in a moment with PGCC with -ACC example. So that's the -ACC is the main flag that you need to have to the compiler to compile with ACC, OpenACC. If you don't do that, these pragmas will not be taken into account, right? So you need to have this flag to take into account these pragmas. You can have additional information with -minfo. -minfo, it's the level of information that you need to have from the compiler and what is happening. And then you can also specify the target here, right? So here we have a target NVIDIA, but you can see that we can have a target multi-core and so on and so forth. And we'll see that in our examples. So here you can see that since we do MM4, the compiler will spit out additional verbosity and information in terms of loop parallelizable, the accelerated kernel is generated, so on and so forth. And that's what you want to see. And if there are errors, you will get information from the compiler and you can address them moving forward. So with that, just this directive, you can start your first OpenACC code, actually. And here is our example, and that we're gonna use today in the DLI from NVIDIA platform. And that's the Jacobi iteration codes, which actually mimic a heat transfer. We'll see the heat transfer example and how it looks like. But basically, you have the calculation here. It's similar to a stencil computation in 2D, and that mimic the heat transfer through a medium. And then you have another loop on 2D where you move the data that you calculated. So you make the calculation based on A as input. That's a two-dimensional array, to an ANU, which is the output of these first loops. In the code, this is the calc function. We'll see it later. And this is the memory transfer or the swap function, where you swap between A and ANU. So basically, the content of ANU after this calculation will be moved to A, and then you iterate again in the next with a very long while loop across 1,000 iteration or whatever max iteration you decide. I think 1,000 is used in this example, in our example, or if the tolerance error is within, if the error is within some tolerance. One important aspect you can see in this code that in the calculation we have a max here. So we calculate the max error across all the data points. So for that, if in some parallelization, we need to put special care on that operation. So max is what we call a reduction operation. So if you do it sequentially, that's easy because every time you overwrite the variable and get always the max. But when you do it in parallel, whether you're using OpenMP, OpenACC, or MPI, you need to add a reduction. So a reduction basically means that you apply that instruction across multiple threads or across the whole parallelism that you have in place in your code. So with that, that's why we add one of the clauses. So I mentioned the clauses are optional annotation that you can add to the pragma. And that's what we do here. So we put in pragma ACC kernels, and we add a reduction clause here for the max. So that's our first OpenACC code. So we compile that, and so I think I went through this, the reduction clause. It will reduce the value to a single value across all the threads. And then we compile it as we agreed and explained before with all the info and targeting NVIDIA here. In our course, we will also do it on multi-core starting in the first module. So that will be also very interesting because that wasn't possible in the very early stages of OpenACC. Now it's supported. All right, so we compile, we have all this output here. You can see that the loops are parallelizable and the line of code. So these numbers are the line of code of your source code. And you can see here that we have accelerated kernels generated. So that's perfect. And you can see even that the max reduction is generated for the variable ERR. So I like those compiler inputs actually and feedback because they help a lot debugging, not only the acceleration, but also the performance. We'll see that the performance can be helped with that, as well as the at multiple levels, from the loops to the data management and so on. So we have a binary, and then we run it on the system. And here are some performance numbers. On previous GPUs, we will update those today. We will update those today with actual numbers on recent hardware. So these are all the hardware. You will see that will be much faster today. So we run it on OpenMP. With OpenMP, because before, as I mentioned, OpenACC doesn't run on multi-core. So today we're gonna run it with OpenACC multi-core target. And you can see here that the execution time improves if you use more threads, obviously. But the issue here that if you look here that the OpenACC code actually is slow. It's even slower than sequential, not even the multi-threaded version. It's even slower than the sequential version. So that's a big failure. And for that, we need to use different tools to identify what are the issues. There are some ancient tools, but there are also new tools such as Insight Systems that we're going to use today. But the initial ones, we used to have a environment variable, PGI ACC time, which give you some information of what is happening. And if you can see here, we are spending most of the time in data transfers. As I mentioned before, that's the discussion between PCI Express links between the CPU and the GPU, how they communicate and transfer data. And the kernel is actually running very fast relatively to a 40 seconds execution or 69 on the sequential. So that's a problem. So we look at it, we look at the code and we try to understand. And what's happening there is that every time you hit an ACC kernel, the OpenACC will have will get the data in, the A as input. And once he finished the calculation, he will get the A new out and copy it out to the host. And that happens on a while iteration. And that's the big problem. So you're gonna iterate over and over again. And you can see it graphically if you use the NVIDIA Visual Profiler here, that you copy the data back and forth, back and forth, back and forth, CPU to GPU, GPU to CPU, CPU to GPU, GPU to CPU, A and NU. So that's the big mess. And that's exactly why I started with architectural details, to understand that it can hinder your performance dramatically. And you can see it with NVProf in the command line or the graphical interface, and Insight now, which is the latest tools from NVIDIA, and we're gonna see it in our DLI. So how to see that? So you can see it in mode zoom. So how to fix that? So the latest PGI or NVIDIA now features that are added is that when you compile, you add managed here. So you add managed here to manage your data automatically. And that will solve the problem with the compiler, if the compiler can manage to fix the problems of the data management. But of course, that's not the best optimal. Data management with the compiler, of course, the compiler has its own limit as much as it can understand as much as it can understand it, the code. Now, if you look at the fine-grained data management, now we go to additional pragmas. Okay, so we have data constructs that is called pragma ACC data, and it has actually very important clauses as features. And those pragmas actually allow you to fine-grain managing the data regions that you have in your code. And with those, you can optimize dramatically your performance. Okay. I see here some comments from our NVIDIA friends about the compiler. I'm showing PGCC here because we're gonna use PGCC in the DLI, but actually those are integrated with the NVIDIA CC and the NVCC, NVC++ that are in the latest SDK. But I'm using, again, still the PGCC now because the DLI actually use PGCC. All right. So data clause is our savior. And let's see what are the clauses that we need to say. So we have 4 main ones. There are multiple features and additional details that you can find in the literature. Go to the latest November 2020 3.1 standard. It's a large number of pages, but you will see all the details about the data clause. So the pragma data clauses could be copy, copy in, and copy out, and create. And very simply put, if we want to explain, the copy is basically copy the data. If you have a data array, you want to copy in as you enter the OpenACC region that you are defining with your data clause, as well as once it exits, once you finish the calculation, when it exits, you copy it back to the host. So you copy from the host to the GPU at the beginning and GPU to the host at the end, but you can specify a whole larger loop of code. So you don't have, so in our case, you're gonna use that across our while loop, right? Not the small loops. Copy in is only on the inputs, as its name suggests, and copy out is when you exit the region as we go out of the region of the data close. So, and that's, so copy out, this would be device to host. And the device is the GPU, host is the CPU, and copy in host to device, CPU to GPU in the beginning. In some cases, you can use actually buffers, temporary buffers, and those buffers, you don't need them on the CPU at all. Neither as input, they are not inputs, they are not outputs, they are just buffers. And basically, you can allocate that data in the GPU using the create clause, or you can use other functions that I will show you later at the end of these slides with OpenACC. All right. Now you can do static allocation, but of course it's not recommended. Static allocation will give the hints to the compiler on the shape and the size of the arrays, but you generally are dynamically allocating data. So if you want to do that, then you need to have the array shaping. You need to tell the compiler what is the shape of that pointer if you have pointers. So that's specifically for C. It's much less of a problem in most of Fortran code, unless it's some edge cases. But basically, what you need to say is you need to give a shape of what you want to copy. So the starting point, if you are sending the whole array, you start from 0, and then you give the size of data that you are sending over. All right. So annotating back to our code, and if we annotate our while loop with the ACC data pragma here, and you can see here that we have now the while loop is becoming our whole data region, which means that data input and output and communication from CPU to host will happen only at the beginning and at the end of this while loop, and not between those two kernels. As you can know, I mean, ANU is already on the GPU. You don't need to move it back to the CPU and back to GPU again. And it can just move on here and be used in the next kernel. And even within the while iteration, you don't need any intermediate data except the error, maybe. So with that, you can say that all this region is becoming one data region with this pragma. Now we look at our usage of the data. So you can see here that A is an input here. It's at the beginning of the loop. And actually, it's the output and has the final results that we want at the end of the loop, of the while loop. So with that, we can declare A as a copy in and out. So that's a copy, right? On the other hand, if we look at NU, is actually, we don't care of its original information, as it will be overwritten with the first results of the first calculation. And we're gonna keep pushing it to A here. So it's basically a buffer and temporary information that we don't need to have on the CPU. So with that, what we're gonna do is that we annotate NU as create. All right. So moving on, and we run this, and with that, we should have better performance. And if we look at the performance numbers, we can see here now that we have a good acceleration. We run on 13 seconds plus, and that's almost 2.9, close to 3 times faster than the CPUs. So that's as expected. And if we profile it now, you can see here that the memory copies are extremely small, and that's what you need to have. So an efficient code should have significantly less memory copies between CPU and GPUs, host to device and device to host. And you can see it graphically that you have only in the beginning here some of the communications, and if you look at the NVIDIA Profiler here, the main bulk of the time execution is on the computes, and those are the different compute functions that we will see, the calculate and the swap functions. And you have only very small communication here on the error that happens on the CPU on the major whitelist. All right. So those are important aspects that we will look at. Now we will look at finer grain optimizations that we can do as well to the loops. So that's chapter 6 that I and Malik we wrote in our book, the OpenACC book, the first one. And chapter 6 actually goes through some different optimization that you can do on loops. So you can make them independent, sequential, you can tile them, so on and so forth. But we will focus on one specific aspect, which is exposing parallelism, right? So depending on the device that you are running, GPU or the CPU or a different kind of accelerator, you will have different levels of parallelism, right? And that's what we are targeting. And if we look at the GPU, for example, we can see here that the run is using thread. The threads are grouped as block, and the blocks are grouped in grid, and the kernel is executed as a grid of blocks of threads. So there are 3 levels of parallelism, and you can know that the thread blocks actually allow cooperations, but if you have multiple thread blocks, then you scale up across the SMs and across all the GPUs that you have, even if you have multi-GPUs. Of course, we are only on the context of one GPU. Multi-GPU programming has a little bit more considerations. So how do we map OpenACC to CUDA, which is what we do on the case of GPUs. We have 3 levels of parallelism in OpenACC that express the same level. So the levels that we can add to a loop are the gang, worker, and vector. And that mapping basically allow to map multiple architecture as well, not only the GPUs. So for GPUs, we can map the gang to the grid, the workers to the blocks, and the vectors to the threads. On a CPU, we can map the gangs to a socket, a CPU socket. You can have multi-socket system, typically 2 in typical servers today. Workers to the cores, and vectors to the symbolization within the core, which is the single instruction multiple data. So in the case of Intel processor, you have 512 bits SIMD instructions, where you can have up to 8 64 bits instructions. So if we look at this, there is also the concept of warp, which is similar to blocks. So we have gang as blocks, worker as warps, and threads as vectors. So that's one possibility. Often there are many cases where we omit the workers and just use blocks and threads because the concept of warp is not very simple to manage. You can let the compiler to do it. As I mentioned before, I mean, OpenACC is descriptive. So you describe and you let the compiler optimize for you as well. So you can manage with just gang and vector most of the time. So basically, the compiler will start with a guess on what is the best possible gang and vectors or gang work vectors description that he can get. But you can explicitly override the compiler execution, the compiler choices, and write your own gang and vector numbers and the way you can lay out your parallelism of the code. And that allows you to tune your applications actually even further. So on a single loop, we can see that's one example here where we have OpenACC kernel loop. We add the loop here, and then we can add the gang and vector pragmas. And in this case, we have 100 gangs and 128 vectors. So basically, we have blocks of threads. But if you use the ACC parallel, which is a slightly different directives, we use instead num-gang and num-vectors. So essentially, we have 100 thread blocks here, and each block has 128 threads in this example. But if you look here at the beginning, we don't know exactly what's happening. So the compiler will tell us what he used. So here we can say probably, I think based on compiler input, there are 16 blocks only with 256 threads, which may or may not be optimal depending on the cases. On the 2D examples, then actually the CUDA blocks can be multiple dimension, and that can be mapped to multiple dimensional nested loops, and that helps a lot. So you can have 200 by 100 gangs or blocks, and you can have the blocks distribution as 32 by 16 threads, 2D threads block as mentioned here in the vectors. And that's useful to extract even more parallelism, as you can see. And as I mentioned further, there are further clauses to the loop clause that I mentioned before, such as independent, sequential, and reduction, which we used. Now, our previous information that we got here is 2.9. Now, we would go back to the compiler output quickly, and you can see here that the compiler told us actually the number of vectors and workers or gangs and vectors that he used. You can see here that he put vectors size 16 and some workers, depending on how it's gonna execute. And we're gonna overwrite those. So what we're gonna do is insert the gang and vector explicitly in the code, and we're gonna change those. And we start playing with the numbers until we get slightly better performance. So actually in our example here, we went from 2.9x, we go up to 3.6x. So it's slightly additional improvement, and we squeeze the best performance at the end from the GPU. All right. So moving on, actually this gang and vector and how we optimize give us an idea, and we put that as a small research project with some of my students, Jazab Siddiqui and Fatma Al-Zayed, and we had a very simple kernel of stencil computation and 3D on this case. But you can see here we tried different shapes, and some of them are weird, some of them are more balanced than others. And you can see here that the balanced one, and what we try to do is we try to automatically auto-tune those. So we had an auto-tuner here where we annotate with different code generation, and then you have different gang and vectors and sometimes workers, and placement within the 3 nested loops of the 3D model. And then we have different variables. So we have A, B, C, D here, 4 variables to optimize, 4 here, and here 5 variables. And we had an auto-tuner that generate those codes and run them just 1 iteration. As you know, those are iterative solvers. So the few iteration we use actually to find the performance of each different parameters and find the best parameters. Once we find the best parameters, we can continue with those parameters. And those actually give us better performance than what the compiler chosen. And that's why we put this optimization. So that's an auto-tuner that we put together. We got here some additional performance squeeze. It go as little as 10. I thought please mute. As 10%, 15%. But it can go up to 2 times and 1.5, 1.8 here on some of the cases. And mostly even cases that are different. So basically the mapping of the compiler is not matching quite well the GPU itself. And actually this tuning actually changed from a GPU generation to a generation. So you can run this tuning. Once you get a new GPU, you run the auto tuner, you get your best parameters, and you're good for the rest of your runs in the future. All right. So with that, I think I have covered most of the information that I want to cover. I think it's time for us to move on. So there are some additional code optimization that we're gonna see, and I don't think I need to cover the runtime at this moment, but what I suggest here, we are getting close to 10. If we have time, we can go through over this runtime, which help us also mix OpenACC with other models, such that libraries and so on. But I will skip that, and I suggest that everyone move on to the modules, and let's try to implement what we learned today in real life on real examples. So what we're gonna do is you go to your DLI. So there's a start button here. Once you started, you get this here. Okay, so that's what it does. Basically, it will launch a VM on the cloud with a GPU, actually. Actually, maybe I can stop it and start it for your sake. So basically, let me try to get a fresh window here. Yeah, so you have a start button here. Probably some of you pushed it. I think I see that one pushed it and he had already a VM. But if you didn't, go to your DLI, push start. It will take a few minutes to load, okay? Once it loads, you will have a timer down. So it will give you roughly 2 hours. Since my time is running out, I restarting it again, such that we can have this. And then once you have your VM set up, you need to push start, and it will give you a Jupyter notebook like this, where you will have the modules that we're gonna run today. So we have 5 modules ranked from 2 to 6. I think module 1 is a very basic one that is omitted now in the DLI. But basically, once you have this, it's still running. It will have this circles. And then once it has, you would get something like this. Then you go to modules. Okay, now I'm out of the, I'm not connected, so everything is not working anymore. But basically, you go to module 2, and we will start working on the first Jupyter notebook. There are C and Fortran options. So let me know if you have this finished and compiled. If you have this, your VM started, please send yes on the chat. If not, let me know if you have any issues, if anyone has issues or something. So I give 2 or 3 minutes for everyone, and I will check back again. Once my my VM is started, I will show you the next steps. Meanwhile, I can answer a few questions. If there are any, please send it to the Q&A or the chat box.
There is one, Saber, in the Q&A.
Oh. Okay. Question: does PGCC and NVC compiler are exactly the same in the latest HPC SDK? Yeah, so that's essentially true. Yes. The only difference is that NVCC compile also CUDA in addition to OpenACC. So basically, in the past, we have a PGI compiler, which you can still download and get, by the way. It still released the latest edition in November, I think. If you go to pgi.com, it's a free edition. Actually, NVIDIA make it free at some point, which is great. It's only the support. If you need the support, you're gonna pay for that. But if you go to PGI compiler, You can even download the latest version, actually. There are releases even in 2022. So here, well, latest release in February, but that's the latest release. I think subsequent release after that are embedded within NVCC. Isam maybe can unmute or share if there is any of the NVIDIA can add any additional information.
So Isam has replied it, but to the panelists, and I think, so he said like the doc is available on the docs.nvidia.com/HPC-SDK. And so you can download by downloading the HPC SDK. So you have all the compiler, the CUDA toolkit, and all the math library into one package. So now.
Yep, here it is.
Exactly.
Yeah, and you can see here that now NVC, the compiler, actually supports multi-core CPU programming with OpenACC and OpenACC. So actually, basically, the whenever you have an OpenACC or previously PGI code, I would say, that can be captured here. And that's the compiler actually covers not only NVIDIA GPUs, that's impressive. So it covers the C11 standard, and it runs even on AMD Intel powered ARM CPUs. And ARM is becoming a very interesting thing for NVIDIA as they are about to acquire it. Yeah, so you can run with NVC compiler. Yeah. Now the NVCC is the CUDA compiler. Now I'm correcting myself. It's not 2-in-1. It's actually the NVCC as previously working as a GPU compiler, the CUDA compiler, and NVC for CPU and OpenACC compilation. And you can have everything with the SDK. Yeah. Today we're gonna use, I think the DLI by NVIDIA is actually using PGCC. So you can see here that we are actually compiling with PGCC, which is the latest release here. Actually, you can check what is the version. But in the future, I would recommend to use this. Hopefully, we'll upgrade the DLI as well. So, oh, okay. So you must have this now launch task arrow in your screen after you have the VM, the virtual machine loaded. So you're gonna push launch task, and basically that gives you the modules that I showed you before, and we're gonna go to module 2 and the English version. Obviously, some of the DLIs have multiple English and some multiple languages, not programming languages, but even languages, some French, Chinese, etc. So we have C and Fortran. You can choose whatever you are comfortable with or whatever your code is to have the learning experience. I'm gonna go with C since I'm a C code. Bilal will go with Fortran for sure. And then you will have, once you enter there, you will have your working space. So you have a Jupyter notebook here, readme.igpynb, the Jacobi code, the Laplace.c and .h. This is the code that we're gonna work on, and these are the solutions of the whole DLI. Don't go to the solution yet. And basically, I have that open before, I did it before, but let's open it again, a fresh one. So you can see here that it's opening an instance on Amazon and AWS cloud. And it will get you through the instructions of various steps that we're gonna use, okay, across the day. This is the first lab. I'm gonna go through it for 5 minutes, and then we're gonna pause for maybe 15 minutes and give you the chance to do it yourself, read through it with the details, and we'll come back after that to look at module 3. So in module 1, and I hope you are familiar with Jupyter Notebook. So basically that's the button you can use for run, or if you are on a cell, you can hit Shift and Enter, and that will execute that cell. And we're gonna go cell by cell and read through it. So the first command here basically give us information on which kind of GPU we are running, okay? And you can see here that we are running on a V100. SXM2 means it's using NVLink. That's a bit additional feature. It's actually the communication between the GPUs, as you can see here. But since you are in a single GPU, it doesn't matter too much for us. And that can give you, remember that I told about the threads and blocks and grid, and that's the size of threads and grids and blocks. So massive parallelism, as you can see here, right? That's we're gonna exploit potentially. So those are the main information that you need typically. That's the memory size, it's 16 gig of HBM memory. Now, what we go is a loop of analyze, parallelize, optimize, and that's a loop on any parallel programming. It's not specific to OpenACC. That's any parallel programming with any programming models. You're gonna do analysis, parallelization, optimization, and that's a key for the hackathon. So the first thing that we're gonna do for your hackathon is to analyze your data, analyze your code. And how we analyze the code is using some tools, and there are different tools that we're gonna go through, and we're gonna learn today. Today we're gonna use Insight. So I'm gonna go. You're gonna see the examples and how to use it. I'm gonna use the command line interface, but we can get more information on the day of hackathon. Actually, we're gonna have a session on Insight. Computing systems, and today maybe we have some also at 12. I'm not sure how it's gonna be exactly, but we're gonna have some of the Insight inputs today at 12. All right, so the analysis part is we're gonna run the code with compile it and run it. So as I mentioned here, we are using the PGCC. In the future, if you want, you can run it with the NVC. And you can see here that we are putting a few compiler flags. So the fast for acceleration, this is the Jacobi code, the Laplacian code. And once it's compiled, we're gonna echo it is compiled, and then we're gonna run it. So that's our binary ./Laplace, and we're gonna run it. So I'm gonna do Shift and Enter. So it's gonna do the compilation, and you can see some of the outputs. It's a small warning, but it doesn't matter. You can fix it if you want, if you have time, but it's not a big deal. And then the computation is successful and start running. So we're gonna run the same Jacobi code that I mentioned. And if you go to module 2, you can see our object is there since we are compiled. You can go to Laplace 2D.c. Those are the functions. So the initialization of A and NU, the function calcNext, which does the calculation that I showed you before. Here, this is the stencil computation for the heat transfer, and this is the error, the Fmax. And then we have here the swap function where we put NU within A. Okay, that's where we move the data. Okay, and then here we deallocate, and here we the codes. Okay, so we have the main function is on Jacobi.c, and that's the main function, and that's our initialization, allocations, etc. We're going to go through this. If you can look at the inputs there, and this is our main while loop. So we have the calcNext and then swap function. Those are our two main functions, and we iterate. Okay, and then we have time gathering as well. So I hope the run is completed now here on the C code. And then it takes 61 seconds. We can take notes if you wish, such that we can see what is the acceleration we are getting as we move forward. So we're gonna analyze the code. I think we went through the code now. Actually, it basically the 2D array, the A is basically this 2D volume or 2D space. And then that's the hotness. We're gonna apply a very hot inputs of temperature, which is called, we will put it as 1, and 0 would be the initial temperature here. which is room temperature, and then we're gonna propagate. And you can see here that's the propagation that we expect. That's how the arrays will start with ones and zeros, and then 0.25 will be calculated, and so on and so forth. So these are the calculation of calculates. If you have time, go through all the details and explanations. It gives you even references to the line of codes on specific examples. Now, if you look at the insight, that's the way that we're gonna do the profiling of our codes using Insight systems. You can download the graphical and install it in your code, but we can use just the user interface and the command line. So here you have explanation how Insight works, and you can. That's an example of reports on the NVIDIA statistics that we can get. If you want the GUI, here is the link from where you can download it and get the file that is generated and open it. So basically, the file generated is this Laplace minus O. Laplace, you can rename it if you want. Laplace dot whatever instance. NVIDIA tool extensions. So those are some additional C-based API that you can annotate events, time range for timing, and so on, and then can give additional hints. So the calc function here, the swap function here, as you've seen in the code, and we annotate those functions to get this information, and then you have the beginning and the end as well. So we run it with a profile here. We generate it and see what we get. So it's the same execution. We didn't do any coding yet. So so far we didn't use the target. We didn't target our run to any device, so it's still running a single threaded, and it will give us some information on the execution time. You will see here that we will find an mcopy8 coming in the outputs. As I mentioned, with the minfo, you get additional verbosity from the system, from the compiler, and if you put opt, it will give you information about the optimization. If you put accel, it will give you information about the acceleration. And if we run here, you can see that okay, next cell cannot run until the previous cell is completed. We will see that why this copy. It's basically one optimization on the swapping of the arrays. Once we do that, we're gonna run with the multi-core, with the -TA multi-core, and that will run on multiple cores. So I want you to run this and tell me what is the speed up that you get from this code on multi-core CPU. And then once you do that, you're gonna do the profiling of the same multi-core code, and you will see the different profile of the code. And that's the end of our first module. However, if you have a little bit time, it takes actually 1 second. This is the Tesla acceleration. Now we're running on NVIDIA Tesla, the V100 here, and you will get at least an information on what is our target. This is our end game, actually, basically, which is the accelerated code, and we're gonna look at this code, how we're gonna go through it in the next modules, and we're gonna run it, and you'll see it straight away, some acceleration straight away, which helps a lot to get some motivation to carry on, to see how we can get this GPU code accelerated on the next modules. And then you profile it again with Insight. So I hope everyone has this session loaded, and we can start running. You can see here, those are the Insight profiling, the proportion of the calc and swap, and so on and so forth. So with that, if there are any questions, please send them to the chat, or I think you can unmute yourself. And I will give you 15 minutes, roughly 10-15 minutes to read through this and run the CPU, sequential CPU multi-core, and the GPU one in the optional part of the bonus task, if you wish. which will be our target by the end. So this is actually the solution GPU code. Please don't look yet at this code yet. We want to build it together step at a time.